I think we're reading chapter 2 today. Yeah.
We're finishing chapter 1.
I got the tutorial question.
Yeah, I want to go to that.
That was your weekend.
Because
Yeah, no, that's the examples we said, I know they're both not there.
Do you know much about your
It's because the one who looked at the class were sailor fields. I don't think that's. I was like, yeah, it's basically. It's so much fun. Would be good, like, where they try to get to. When's the assignment?
Soon-ish.
You can take it,
If I can manage it, I'll probably get it done for Wednesday's class. I'll get it posted. Okay, so. All right. Good, so I hope everyone had a good weekend. Let's get started. If you haven't noticed already, the tutorials, the group problems and the solutions and the quiz and its solutions will appear on the course website after the tutorial session. So either Thursday evening or maybe sometime on Friday. So the format will be the same going forward. So you'll do about 40 minutes of problem solving, working through problems relevant to the material that we've covered recently. And then there'll be a little individual quiz the idea of the quiz is that it's not a long calculation. It's something that you can answer quickly, maybe multiple choice or like a one-line kind of answer. So that's what we're gonna do. And oh yeah, the other thing I wanted to say about the problem sets is don't feel like, if I give you 5 problems, don't feel like you're supposed to be able to get through all of them in 40 minutes. That's not the intention. The intention is that I give you enough material that you'll stay busy for that 40 minutes that you're working on it. And B is that the stuff that you don't get to in the tutorial are just extra problems that are low stakes, like they're not worth grades, that you can use for practice, and then you can compare your solutions to mine to see if you're on the right track, or maybe you come up with a different method for solving the problem that reaches the same final answer. That would be good too. Okay, any questions about that stuff? Yeah.
One of the curl question from the tutorial quiz was similar to one of the cases that we covered in class.
Yeah.
It's 0.
Yeah.
I can really tell why the answers are different.
Oh, yeah, okay, so the reason it was different is because the case we did in class, let me do the point charge, the divergence of a point charge. That was, we took the divergence of 1 over like r squared. We're going to do it again today, actually. So that one is exactly 0 everywhere except right at the point charge. The problem I gave you in the tutorial was you have a uniform distribution of charge inside some sphere or something, and we're going to look at the electric field or some vector field inside that sphere. So that's a little bit different, right?
It's also, if you think about the case where it'll be 0, it's decreasing as it's decreasing.
Yeah, the one we did in class, the magnitude decreases as you move away from the charge.
This one was
increasing.
increasing as you went further away from the center.
Yeah.
Same with the curl.
Okay, but yeah, we can discuss that more. So what I want to do today is I want to, I hope, finish off chapter 1 so that we can get into the electrostatics chapter 2. The thing we were talking about last before we left for the weekend, well, in fact, this was maybe Wednesday of last week, was Stokes' theorem, which is the curl of some vector field integrated over some surface is the same as that vector field integrated around the boundary of that surface. And I've tried to draw that here. This is like some surface in 3-dimensional space. It's like a little bubble. Maybe this red line is some kind of loop that you've dipped into a soap solution, and then you slowly swing it through the air, and this little bubble forms. So that's the surface, and then the red line is the boundary. I'm going to assume that you know how to evaluate surface integrals, line integrals, and volume integrals. But let me just remind you what the .dA means. dA represents some little patch, some infinitesimal patch of area on your surface. And then, so that's the magnitude, is the area of that patch. And then it has a direction that is normal to that area. So for a surface that's not closed, that normal direction could be, there's 2 perpendicular directions, right? There's one that is pointing upwards here, and then there'd be one that's kind of pointing downwards. So the way that we are going to resolve that ambiguity in Stokes' theorem is by the right-hand rule. So if I'm going to do this path integral in the direction that's indicated here, I could curl my fingers along that direction, and then that tells me the normal vector for my patch is going to be up. If I reverse the direction of the line integral, then I have to also reverse the direction of my dA. Okay, so what I want to do is I want to imagine taking Stokes' theorem and applying it to Ampere's law. So this is the one form of Ampere's law that you would have saw in like a first year E&M type course. It's the line integral of B dot dl is mu naught I enclosed. But that's exactly the right-hand side of Stokes' theorem that we've written up there. So we should be able to re-express that as the curl of B. And so this line integral around a closed boundary is the same as the curl of B integrated over some surface that has that boundary. And then that has to be equal to mu naught I enclosed. And then what we can imagine doing is saying, well, if I did have some material, like maybe this is some conductor or something, a wire, and there's some current distribution in that wire. So this is a current density or current per unit area. And it's going to impinge upon this surface that is inside of our wire, then the total current is given by this dot product of the current density across the surface. And so we can replace I enclosed with this thing. And so then we have this curl of B dot dA is, instead of I enclosed, it's the surface integral of mu naught times J. But now we have the same integral, and so the integrands have to be equal. And one of Maxwell's equations for static electromagnetic fields is the curl of B is equal to mu naught J. And so that's, if you summarize all of the things that we did last class and today for Maxwell's equations, we've written down the 4 Maxwell's equations already, just based on some of the vector calculus that we've covered. The qualifier is that these are for electrostatics, or fields that aren't changing. One thing we'll do is we will try to revise these to incorporate the cases where the electric and magnetic fields can be changing with time. Okay. So I'd like to try to do that. I'd like to well, okay, maybe not. Okay, I'll save this for another time. I'm tempted to do it, but then we won't finish the chapter stuff. Okay, so let's leave that for now. We'll do it another time. But I'll just tell you that Faraday's law tells us how changing magnetic fields and electric fields interact. Faraday's law says the time derivative of the magnetic flux is equal to induced voltages, but induced voltage differences are caused by electric fields. And so that tells you at least that a changing magnetic field can create electric fields. And that's not captured in this set of Maxwell's equations. And so they need to be revised. The opposite is also true. A changing electric field will create magnetic fields, and that's not captured in this set of Maxwell's equations. Okay, so let's do Griffith's 1.4, and this is curvy linear coordinates. Now you've already told me that you covered this in Math 317. So what I'm going to do is I'm not going to do everything. I'm going to give you a bit of a flavor for how some of this stuff works. Okay. And essentially what we're going to do is we're going to say, look, if I have some point in space, in three-dimensional space, I can specify it with three coordinates. The standard ones are x, y, z, and those are the Cartesian coordinates. But that's not the only way I could represent a point in space. I could come up with other coordinate systems that have mutually perpendicular unit vectors that equally well specify that point. And so we're gonna look at spherical coordinates specifically. The other commonly used coordinate system is, of course, cylindrical coordinates. But the reason I choose to do spherical coordinates for our examples is because it's the harder one to work with. The cylindrical coordinates are just polar coordinates in the XY plane and a Z axis. So those are more familiar. So let's do the one that's a little more awkward. So spherical coordinates. So rather than specifying the position of a point by x, y, z coordinates, we can use a different set of coordinates with mutually perpendicular unit vectors. Okay, so one such system is spherical coordinate system. Okay, so now we're going to test our ability to draw, and let's see how we do. So I'm going to draw our usual Cartesian set of coordinates. So this would be our x-axis, here's our y-axis, and here's our z-axis. And I'm just going to pick some point in space. So I'm going to draw a line from the origin of our coordinate system, and I'm going to go out to some point P. Right. So we could just find the x, y, and z positions of this point P, or we could say, let's find the distance from P to the origin. So that's going to be one of our coordinates. Okay, so we've already did that. Okay, so R is going to be the distance from origin O to point P, and so here our origin is sitting over here. Okay, and we can define our r hat unit vector as just being along that radial line. So this is r hat. Okay. The other thing we could do is we could say, let's specify the angle from the z-axis to this radial line theta, and we'll call that theta. Now we have a coordinate that doesn't have units of length, right? It has units of radians in this case, and so that's already a little bit different. So theta is the angle between z-axis and the radial line to point B. The way you specify the unit vector is if you were to draw a perpendicular from this radial line at point P, that's kind of giving you the sense that this thing is rotating. So this will be perpendicular, and this will be our theta hat. Next, we have something that's slightly more complicated. What we're going to do is we're going to project this down into the XY plane such that this is perpendicular. And this line that lies in the XY plane is r times sine of theta. Because, you know, that same line sits up here. And so that's the line that's opposite of angle theta, and so we'll use the sine. Okay, so our third coordinate is going to be another angle, and it's going to be phi. And this is the angle that's measured from the x-axis to the projection of the radial axis in the xy plane. So phi is the angle between x-axis and the projection of the radial line into xy. All right, now we need a unit vector, and it's going to be the same thing. It's going to be perpendicular to this projected line, r sine theta, and it's going to give kind of a sense of rotation of phi. And so this is the hard one to draw, but it's going to be something like this. This is phi hat. And what we have to imagine is that that is perpendicular to the r hat unit vector, and I can't draw it. It's also perpendicular to the theta hat unit vector. Okay. So what we're going to do is we're going to try to come up with a way of converting between, say, our usual Cartesian coordinates and these spherical coordinates. So since r in Cartesian coordinates is x plus x hat plus y times y hat plus z times z hat, we want to find a relationship, or let's say relationships, between x, y, z and our new coordinates r theta phi. All right. So let's start with the easy one. If I want to find the z coordinate of this point P in terms of r and theta, well, that's pretty straightforward, because what I have here is that Z is equal to R. This is the Z axis is the angle adjacent to, or the side adjacent to theta. So this is Z cos theta. So that's the easy one. What about the x coordinate? If I draw a dashed line here, now what I have is this is supposed to be a perpendicular. And I can use those. So this x distance is what? This position is adjacent to the angle phi, and r sine theta is the hypotenuse. Yeah, it's r sine theta cos phi. And so I need a little more space to write all that. So this distance here is x is r sine theta cos phi. And along the y-axis, well, it's this length here that is the side opposite of phi. So we're going to get sine phi factor. So y is r sine theta sine phi. Okay, and so there's all of our expressions x, y, and z written in terms of our spherical coordinates r, theta, and phi. So we have x is equal to r sine theta cos phi. Y is equal to r sine theta sine phi, and z is equal to r cos theta. Okay, and so that means that we could write our position as as r sine theta cos phi x hat plus r sine theta sine phi y hat plus r cos theta z hat. Okay, what we need now are relationships for expressions for our unit vectors. We drew on our diagram here r hat, phi hat, and theta hat. And so how are they related to x hat, y hat, z hat? Okay, so let's try to express r hat terms of x hat, y hat, z hat. And it's going to turn out to be the same sort of drawing that we just analyzed. And so we could do this a little more quickly. So we're going to have, oops. Usual x, y, z axis. And then we'll just draw like an r hat unit vector. So some radial unit vector that's pointing out in space somewhere. We'll label our angles. There's the theta. We can project this down into the xy plane. And here is phi. The r hat unit vector has a length 1. All unit vectors have length 1. And so the magnitude is 1. And so now we're just trying to specify directions in terms of these angles. Well, if we extend back to the z-axis here, start with the z-axis, because then again, that's the easy one. This is the side adjacent to theta. So this is cos theta. Projection down into this plane is sine theta. And if we find the xy coordinates, the x-axis is going to be sine theta times the side adjacent to phi. So it's that cos phi. And sine theta. So if I want to write a vector equation for r hat, well, what does it do? It goes out this distance along the x-axis, and so it's sine theta cos phi x hat plus this distance in the y direction, sine theta sine phi y hat plus cos theta in the z direction. Okay. So that's one way to write one of our unit vectors in terms of the x, y, z unit vectors. I'm not going to do all of the other ones for you. We can do the other ones and you would get the following results. Likewise, we can show, and this is a problem in the textbook, it's 1.38. So we've done 1/3 of that problem. Theta hat, you could write as cos theta cos phi x hat, whoops, plus cos theta sine phi y hat minus sine theta z hat, and you could write phi hat as minus sine phi x hat plus cos phi y hat. Phi hat has no z component, and you can see that because the way we defined phi hat is it's a rotation in the xy plane, and so its unit vector sits in that plane, and so there is no z component. So here are those expressions again. The other thing that we'll need to do is we'll need to integrate in the spherical coordinates. And, you know, for example, if you want to do a volume integral in Cartesian coordinates, your d tau, your element of volume, is dx, dy, dz. And that's just because dx is just a linear displacement along the x-axis, dy is a linear displacement along the y-axis, and dz along the z-axis, and that defines the edges of a cube. The volume element in spherical coordinates is a little more complicated. So let's consider an infinitesimal volume element in spherical coordinates. Okay, so again, we're going to really stretch our ability to draw, or at least my ability to draw. So x, y, z. Okay, so we start by imagining we just have some point in space that's distance r away from the origin. And then what we're going to do is we're going to imagine taking an infinitesimal step along the r hat direction. And so that step is going to be a step of size dr. Okay, that's fine. Then we have, this is our angle theta. Now we're going to take a little step in angle d theta. So we're going to go theta to theta plus d theta. And if I do that, you know, I'm going to get this new radial line that's going to sit over here. And inside, we're going to have our d theta displacement. And that's going to bring this edge of our little volume element. What's the length of this edge? D theta is in radians, but this edge has to be measured like in meters. So what is it?
It's this small angle approximation, right?
Yep.
R over
So it's just this little arc length. R times d theta is what it is. Yeah, so in fact, it's not even a small angle approximation. Think of the circumference of a circle is the radius times the rotation, 2 pi radians. Half a circle has a perimeter of r times half the rotation, so that's pi times r. And so if the d theta is just some value in radians, it creates an arc length that is r times that angular displacement. Okay, well, that kind of defines for us a little area. And so we need to turn that into a volume. And the way we do that is our usual like little projection down into the XY plane. And then here's our angle phi. And now we imagine taking a step d phi. That's going to be something like, I guess I'll use green. D phi sits something like this. And that's going to define this arc. But we have to be a little bit careful because the length of this projected radial line is r sine theta. And so this green thing is the radius, which happens to be r sine theta times d phi. Okay, and then that goes up here. And so now we're going to try to draw this three-dimensional volume element in space here. And this is the little piece of arc here. And so this is our volume element TB. And its size is the edges of this kind of cube-like object. So dr is one edge. R d theta is another edge. And r sine theta d phi is the third edge. We could check that it has the right units. It has to have units of length cubed. R is length squared, and then dr is length cubed. And so usually you'll see this expressed as something like r squared sine theta. I don't know, how did they do it? Dr theta d phi or something like that. So that's our little volume element in spherical coordinates. Okay. What I want to do next is I want to think about how to take these vector derivatives in spherical coordinates. And so it's maybe not a hard problem, it's a long problem to work out. So I'm going to give you some of the steps of that problem, and then the motivated students could go work out the rest of the details. Okay, so let's consider the del operator, our del derivatives in spherical coordinates. You probably have already looked, or I mean, you've probably seen already what these look like, and they're complicated, right? So there's different rules for taking the gradient, the divergence, and the curl in spherical coordinates, and some of the expressions get a little messy, and I'm going to show you where that mess comes from, or part of it anyways. So the types of things that we're thinking about doing is the gradient, or the divergence, or the curl, or the Laplacian. So we're not going to do all of them. We're going to touch some aspects of the gradients. Okay, so we start by writing down the gradients in Cartesian coordinates. Right, we know how to do that. the gradient of some scalar function is the x derivative in the x direction plus the y derivative, the y direction plus the z derivative, z direction. Okay, and then so we say, now we face our problem, we say, okay, what if my scalar function is expressed in terms of spherical coordinates, so it's in terms of r, theta, and phi. Well, one approach is just to say, forget that mess, just take your scalar function and redefine it in terms of x, y, z, and then you could just do these derivatives, okay? But maybe for some, maybe there's a good reason why you don't want to do that. So if t is expressed in terms of spherical coordinates such that t is a function of r theta phi, well, then what's going to happen is we're going to have like dt by dx. So this is now just the x derivative. So everything we would do for this x derivative, we would have to repeat for the y and z derivatives. But let's just see what it looks like. Now this is going to be a function of r theta phi instead of x, y, z. What would you have to do if you want to actually evaluate this derivative without switching to x, y, z coordinates? Chain rule, that's right. So we have to do chain rule, and chain rule says that we would do, let's see, dr by dx times dt by dr. That would be for the r coordinate, and then we have similar terms for theta and phi. So this is chain rule. Now that looks pretty nasty, and it is a little nasty because now we have to do like the dr by dx, d theta by dx, and d phi by dx. And that's not so trivial because we have so far written down x, y, z in terms of r theta phi, but we need the inverse of that in order to make some progress. So let's see how that would work. Okay. So let's start with dr dx. Okay, so we know that r squared, well, okay, let's not do r squared. We know that r is equal to the square root of x squared plus y squared plus z squared. Okay, so that means dr dx is d by dx of square root of x squared plus y squared plus z squared. Okay, well, we could do that. It's another chain rule thing, but we can manage it. So it's going to be 1/2 of something over the square root of x squared plus y squared plus z squared. Okay, because we have all of that to the 1/2 power. The derivative reduces the power by 1 to minus 1/2. So it goes in the denominator. And then we have to take the x derivative of what's underneath the square root, and that's just going to be a 2x. So this is going to be 2x. And so we end up with x over r. Okay. But x over r, if you look here, where's x? X is r sine theta cos phi. If we take x over r, it's just sine theta cos phi. So what we have then is This is sine theta cos phi. And so therefore, we've done one of them. dr by dx is sine theta cos phi. This is one of the 9 derivatives that we need. We need 9 because we're gonna need d theta dx, d phi dx, and then we're gonna need dr dy, d theta dy, and so on. I'm not gonna do 9 of them, but I've done the easy one. Let's do one of the more challenging ones, and then that's where we'll leave it. Okay, so next, let's consider. Well, the next one we have to do is say d theta dx. Okay, so how are we gonna do that? D theta dx. So first, let's think about x squared plus y squared. Okay, x squared is, you can see x there. X is r sine theta cos phi. So x squared is r squared sine squared cos squared phi. Okay, then y was r sine theta sine phi. So if we square it, we get r squared sine squared theta sine squared phi. Okay, so this is x squared. This is y squared. Now what we have are some common factors. We have r squared sine squared theta, r squared sine squared theta. So that's r squared sine squared theta, and then we have cos squared phi plus sine squared phi. And so that's 1. Okay. So therefore, what we can do is we can say sine squared theta is equal to what? It's x squared plus y squared divided by r squared. So if I take the square root, I hope you will last a while longer. So it's going to be square root of x squared plus y squared by pi r. Okay, I wonder, did I write it down?
The judging had one.
Yeah, the thing is, I would need a. This is old, so it's the Apple proprietary thing, what do they call it, Lightning? Or something like that.
I gotcha.
Oh, yeah, nice. Oh, sweet, so you have both, you have the US, no, this is USB-C. Oh, I see, it's got the other end.
You want a block as well, or?
Yeah, I do. Thank you very much. Right, sweet.
Do you want to keep it in the spirit and cancel out the other?
I can't cancel out the r because r is x squared plus y squared plus z squared. I don't have the z squared here.
And so sine squared theta times the r squared.
What I want is I want to write some kind of expression for theta in terms of x, y, and z. And I can't do it directly, like I could take the inverse sign here, but I don't want to do that because I don't want to take the derivative of arc sine of all of this crap. So I'm not going to do that. What I'm going to do is I'm going to say, okay, let's try d sine theta dx. Okay, and let's remember that we've already worked out dr dx. Okay, so d sine theta by dx is going to be equal to what? Okay, I'm gonna treat this like a product rule. So we're gonna get 1/r. And then we take the derivative of this thing. So what's that gonna be? It's gonna be 1/2 times 2x divided by square root of x squared plus y squared. Somebody's gonna have to tell me if I make a mistake, because I like to make mistakes. Okay, so product rule says then we have to add to that the numerator that we have. And then I have to multiply by dx of the denominator. Well, it's 1/r. Okay, so what are we going to be left with? This is 1/r, and then we have x over square root of x squared plus y squared, plus square root of x squared plus y squared. And then what are we going to get? Minus 1/r squared dr dx, I think. I think so. Okay. So we know already that this is sine theta cos phi. Okay. What else could we do? Let's see, this is 1/r x over the square root of x squared plus y squared minus x squared plus y squared over r squared sine theta cos phi. And so you can see it's already looking pretty nasty. Okay. So what could we do next? We could say we still haven't done the left-hand side because we want ultimately d theta dx, not d sine theta dx. So on the left-hand side, d sine theta dx is, what's the derivative of sine? It's cos theta, and then we're going to have d theta dx. So we want to solve over d theta dx. Okay. So what are we going to have to do? We've already worked out x squared plus y squared. It's right here. I think this is what you were talking about. X squared plus y squared is r squared sine squared theta. So we can use that here and here. And I already know x is r sine theta cos phi. And we're going to use x is r sine theta cos phi. Okay, so let's sub that in. So therefore, cos theta d theta dx is equal to 1/r. X is r sine theta cos phi. X squared plus y squared square root is r sine theta plus, minus x squared plus y squared square root, so that's r sine theta. Divide by r squared, and then we have sine theta cos phi. Oh, there you go. Okay. All right. Cancel and r, cancel r. And what are we gonna get? I hope we get something useful. Okay. So this is 2 sine theta cos phi. Oh, sorry, we do more cancellation. We have sine thetas cancel. So then what do we
Cancel
get?
it.
Would-
Never mind.
Is there more?
Nope.
No, okay, okay, so this is going to be cos phi divided by r minus sine squared theta cos phi divided by r. And so that is going to be cos phi over r. We have 1 minus sine squared theta. What's 1 minus sine squared? That's right, cos squared theta, cos phi over r, cos squared theta.
Cancel it.
Yeah, now we can cancel. What a freaking disaster. Okay, so there we go, cancel the cosine. And so therefore, finally, d theta dx is equal to, I'll write it as cos theta cos phi over r, and that is indeed the correct answer. So this is now 2 of 9 required derivatives. What you would have to do is you would have to keep going. So keep going. I did one more, but I'm not going to write it down. I did the d phi dx. So the way you would do d phi dx is you would go, I won't write it down, but I'll give you a hint. You go back to here and you say, all right, where the hell is it? Here it is. If I take the ratio y divided by x, the r's will cancel, the sines will cancel, and we'll get tan of phi. And so what you could do is you could do like chain rule, you could do d by dx of tan phi. That's going to be 1 over cos squared phi d phi dx, and then you have to do all of this similar sort of stuff that we did for the theta case. Okay, but I won't do that. What I'll tell you is the answer. If you try d phi dx, you should find the following results. And so I'll leave this as a challenge for you to work out. You should find the following results. Anyways, if you do all of that, then you combine everything. We could say then that the x derivative of t, when t is expressed in spherical coordinates, is sine theta cos phi dt dr plus cos theta cos phi over r dt d theta minus sine phi over r sine theta dt d phi. And that's just the x derivative. Still need to do. Still need dt dy to be said, and I'm not going to do that. Okay, I'm not even going to write down the answers for you. But if you do all of that work, you can finally show that the gradient of t in spherical coordinates is going to be t dr r hat. That one is trivial, right? That one is no different than, like, say, the x component in Cartesian coordinates. But then it gets different. And you know it has to be different because it couldn't be just dt d theta phi hat. Like, why couldn't it be that? What's the obvious reason why that can't be right? what do the units of the gradient of t have to be?
Distance.
So the t can have whatever units, like we don't know what that function is, that could have whatever units, but what does the gradient introduce unit wise? It has like d by dx and d by dy and d by dz.
1 over distance.
1 over distance, right? Think of the d by dx is like a change in t divided by a change in x. And so the change in x in the denominator has to have 1 over length units. This one clearly does have that, like the units of whatever t is divided by the units of r, which is a length. So this couldn't possibly work because that's going to be inconsistent unit wise. So it has to have something out front with a 1 over r. And so too does our phi component, right? Our phi component cannot be just dt d phi hat, because that doesn't have the right units. There has to be a 1 over length out front, and there's a 1 over r, but this one will also have a sine theta factor in the denominator, and that's the gradient. And that's the easy one. Like imagine now doing the curl, or God forbid, the Laplacian, which has 2 derivatives, right? But anyways, that's how you could work them all out. Griffiths says that there's a faster, more technical way of doing it, and he's written an appendix that shows you how to do it. So if you're interested, you could look that up. But this is the pure brute force way, and we did 2/7 of the work. All right. Any questions about that? No. So I'm not going to expect you to maybe reproduce all of this. Maybe if I'm feeling mean, I'll put some of this as a homework assignment. But what we'll typically do is we'll rely on the expressions that are given on the front cover of Griffiths. And actually, he has some expressions on the back cover. Okay. Now I have a question for you. Have you studied the Dirac-Delta function in any course?
No, but I've heard it mentioned in some quantum textbooks.
So you've come across it in a quantum textbook, but you didn't use it in like physics 200 or something like that. Okay, so then I have the privilege of introducing to you the Dirac-Delta function. It is a kind of a strange object, but it's pretty powerful once you become friends with it, okay? So what I want to do is I want to consider this vector field r hat over r squared. You can think of this as the electric field of a point charge, right? The electric field of a point charge is kq divided by r squared in the radial direction. So I'm just not going to write down the kq because I don't want to keep writing down constants that aren't going to do anything for us. What I care about is that this is in the radial direction and it is,
Is the power problem?
yeah, there you go. Good job. All right. So hopefully I'm not draining this faster than we charge it, but we'll find out. So I'm interested in this radial direction and the 1 over r squared dependence. So this we'll just write down, this is proportional to the electric field of a point charge. And so if I was to plot that vector field, I'll plot it just in 2 dimensions, but it would be this kind of thing where, it looks like if anything should be diverging, it is this function. But as we already know, the divergence of this is 0 almost everywhere. Okay. So in spherical coordinates, the divergence of this vector field V is given by, so I only need the radial component of the divergence because my vector field has only a radial component. We used this already last week sometime. And so the radial component of the divergence is given by this expression. So this is the radial component. And then this VR is just 1 over r squared. And you can see immediately that the r squared is going to cancel with the 1 over r squared, and we're going to have a derivative of 1, which vanishes. Okay, so this is equal to 1 over r squared d by dr of r squared over r squared, and so this is 0. So therefore, the divergence of V is equal to 0 everywhere except at r equals 0, where clearly 1 over r squared diverges. Okay, so fair enough, we saw that already, but now we have a new tool in our back pockets, and that tool is called the divergence theorem. So let's try applying the divergence theorem to V. Okay. Well, what is the divergence theorem? First of all, it says the divergence of V integrated over some volume is equivalent to the surface integral of V. And that surface is the surface that bounds the volume. And you know, we could pick whatever volume with whatever surface we want. I'm going to make a choice that is simple. I'm going to choose a spherical volume of radius capital R. So let's do this calculation for a spherical volume of radius capital R with the origin at the center. So if I was to draw that, so we're going to have our origin here, and then we'll have some kind of sphere that's surrounding this origin, and we'll give this sphere some radius capital R. All right, so let's see, let me draw a bigger sphere, because I said that I'm going to assume that you can do like these surface integrals and these line integrals and so on. Let me just remind you about some aspects of these surface integrals. So, oh god, sphere. Okay, so it's still not great, but it's a little bit better. So what we'll do is here, I'll try to indicate that this is a three-dimensional volume coming out here. And I want to consider like a little patch of area on this sphere. So this is a patch of area, and for closed volumes, the dA, is here. I'll put this. So we'll write dA vector is dA is the size of the area, and then has a direction that's normal to that area, and so it's this n hat. For a sphere centered on the origin, this n hat will always be in the radial direction. So for our spherical volume. N hat is equal to R hat, and so therefore our dA is going to be dA R hat. And let me just remind you that when you have a closed surface, if you're trying to find the direction of dA, it always points outwards by definition. Okay, so what we're going to try to do is we're going to try to do the right-hand side of Stokes' theorem. That's why I spent time trying to write down that dA. So the right-hand side of Stokes' theorem. Okay, right, so it's just V dot dA. And so this is over our surface. V is R hat over R squared. dA is dA, the magnitude dot R hat. So clearly R hat dot R hat, that's just going to give one. A vector dotted with itself gives its magnitude squared, but unit vectors have length 1. So we have S, then we have dA over R squared. Okay. What's dA going to be? Well, what we have to imagine is, let's see if we can go back to our spherical coordinates. We wrote down our little volume element. Which part of this is not changing over top of our sphere, on the surface of our sphere?
Radius.
The radius, right? So there's no dr, but the rest of it is there. So this r squared sine theta, d theta, d phi is the size of our little patch of area on our sphere. So let's see, on the surface of the sphere, R equals capital R is constant. And dA is equal to R squared sine theta, d theta, phi. Okay, yeah.
So just R being constant, wouldn't dr be 0 then? Would that equation go to 0?
Oh, yeah, but I'm not, so that's right. That expression was for the volume element. But I'm now thinking of just one side of that on the surface of the sphere. So that, I mean, that piece of surface area does have 0 volume, but it doesn't have 0 area. Right? Yeah. Okay, so what we're gonna do is we're gonna say, all right, we're at a constant radius r. So wherever we see a little r, I'm going to replace that with capital R, and this dA is going to be this stuff with the capital R. Okay, and so then our surface integral becomes, let's see, dA is going to be r squared sine theta, d theta, d phi, divided by r squared. That cancels, and so we have to evaluate this integral. Now, our surface integral is a double integral. It's going to be an integral over theta, and there's going to be an integral over, here, I'll draw it over here. There'll be an integral over phi, and then we're going to have here sine theta, d theta, d phi. So all we have to do is we have to make sure we get the limits of integration correct. Both of these are going to start from 0. And let's go look at our picture. She would scroll smoother. Okay, so, oh, that's my R hat. Here, let's go. if I wanted to trace out a sphere with this thing. One way to do it would be to take theta and go from 0 to pi. And that would sweep out the perimeter of a semicircle, or in fact, the area of a semicircle. Okay, so imagine sweeping this thing around, keeping phi fixed. We're just going to get half of a disk. And then we take that half disk and we rotate it 2 pi about the z-axis, and that will sweep out the whole volume of the sphere. So our limits of integration are theta is going to be 0 to pi, and phi will be 0 to 2 pi. And so that's almost always the case when you do these integrals in spherical coordinates, if you're integrating over, say, a sphere of some shape, some size. Okay, so now we've reduced our kind of surface integral, which had this dot product and vectors. Once we evaluate the dot product, it just becomes a regular, ordinary double integral of some scalar function. And so we could do this a little nicer. We could say, look, I can take the stuff that involves theta, and that will just be in the theta integral. I'll take the stuff that involves phi, and that will just be in our phi integral. The integral of d phi is just phi. Between the limits 0 to 2 pi is just going to be 2 pi. And the integral of sine is what going to be minus cos, evaluated between 0 and pi. And so this is going to be, I heard someone say 2 already. So minus cos of pi is going to be plus 1, minus cos of 0 is going to be plus 1. So this is 2. And so our integral of v dot dA is 4 pi. Now, by Stokes' theorem, therefore, this integral, sorry, yeah, you're right. Thank you. Stokes' theorem is for the curl. This is by the divergence theorem. This surface integral is equal to the volume integral of the divergence. And that has to all be 4 pi. But we've already said that this thing is 0 everywhere except at one point. This is 0 everywhere except at the origin. And so what we end up doing is defining a new function to be able to handle this case and make the divergence theorem consistent with the fact that this is 0 everywhere except at one point. So we're going to define they give it a name, don't they? They call it a generalized function, which is going to be called delta R. So called the delta function, conveniently. Such that, well, okay, so it's defined to be the divergence of r hat over r squared. You know, exactly the vector field V that we started with. Okay, this is, I should give it its full name. This is the Dirac-Delta function. And I'm going to introduce one more thing into this definition, And it's a factor of 4 pi. In fact, I'm gonna put 1/4 pi. Okay. Or if we wanted to, we could write the divergence of r hat over r squared is equal to 4 pi times this so-called delta function. And the reason I'm gonna do that is because what we're gonna do is we're gonna end up putting this thing into here for the divergence of B. Okay, so let's do that. I know we have, what, we have 2 minutes left. Okay, so we can get one result here. So let's sub the Dirac-Delta function into the divergence theorem of, and what we'll end up with is the divergence of B integrated over some volume, in our case, a spherical volume, is the same thing as 4 pi times, so this is the divergence of r hat over r squared, which we define to be 4 pi times this delta function, is equal to, integrated over some volume, has to be equal to 4 pi. Because we've already shown that the surface integral gave us this 4 pi factor. Well, we have 4 pi on both sides. So we can cancel those factors of 4 pi and say that the delta function integrated over some volume has to be equal to 1. And this is our first important result about the Dirac-Delta function. And so what we'll do next time is I've got, just a little bit more to do with this delta function. So we'll review this and then we'll do a couple other things. The interpretation is the following. This integral tells us the volume under this function. This function has a volume equal to 1. But the actual value of the function is 0 everywhere except at the origin where it diverges. So it's has an infinitesimal width in 3 dimensions, so around its axis. It has infinite height, and it has a volume of 1. It's a bit like, it reminds me of, do you know this French horn problem in math where you find the volume and surface area of the 1/x function? And so what does it have? It has like, I forget does it have it has infinite surface area, but a finite volume. And so what people say is like, oh, I can't paint the inside because the surface area is infinite. I don't have an infinite amount of paint, yet I could fill the whole horn up with a finite volume of paint and not cover all of its walls. Like, it's that weird problem, right? So this reminds me of that. So just remember, it's infinitely tall, infinitesimal width, but it has a finite volume of 1. And so this is going to have lots of useful properties that will help us evaluate otherwise difficult integrals.
So it's kind of like it doesn't necessarily have a real world significance, but when applied to certain problems.
What it's going to be is like, suppose you wanted to say, like, what is the density of a point particle? A point particle has 0 volume, but finite mass. And so what's its density? It's a finite mass divided by 0 volume, so it diverges. And so you could express the density of a point particle in terms of a function like this. Yeah. Or the charge of a point particle. Charge density. Yeah. But you could argue all those things like, does that actually represent a physical property, like,
It's just like,
we don't physically have tiny point particles, right? So,
I guess it's kind of like a complex number, there's no real world significance, but it's used to solve mathematical problems that you do.
yeah, I think that's probably fair, yeah, yeah. But it has some other properties that we will look at